you. Hello, everybody. So my name is Zahra. Sorry, my nickname is Vida. Sorry for confusion. I know that some of you didn't know that this is me that's gonna present. Yes. Today I'm going to talk about my master thesis, which is about modeling of dust emission for a crusted surface. As you know, that dust storms are frequent phenomena in New Mexico, and most extreme dust storms usually happen in southern part of New Mexico. And according to NMSU crash data, dust storms are responsible for more than 246 crashes from 2008 to 2012, that we had too many injuries, like 28 injuries in that time. There have been several problems in different places in Asia, Africa, and Australia. So several dust emission schemes have been developed to predict dust storms. And all these developed dust emission schemes have been tested against field measurements from different areas. But the thing is that our data source area in the region are often partly crusted. And this means that most of these dust emission schemes have not been tested against crusted surface. So this is why we try to look at these surfaces. So first of all, I'm going to go through some definitions, and then I'm going to talk about dust emission mechanisms and for sure the objectives of the project. And then I'm going to talk about the studies that have been done in this major, and take a quick look at the study area, and I'm going to talk about numerical experiments and results. What's alien process? Alien process is the wind-driven emission, transport, and deposition of sand and dust, and dust by wind. And it means that for this process, we need a sufficient supply of dust and for sure wind to move them. And then we have dust emission rate, which is the vertical mass flux of dust at the surface. It's really important to determine dust emission rate, because dust emission is a key component of the global mineral dust cycles. It means that when dust moves by the turbulence, dispersed by the turbulence, it's gonna carried over the long distances by wind, and then it's going to be deposited in different regions. It means that we're going to have deposits of dust emissions in the main region of this wind erosion, and it means that we're going to have land degradation in the agricultural area. We're going to lose fine particles that are really important for the agricultural lands, because they are source of organic matters and also some other good materials. And also, dust produced by wind erosion is a major source of atmospheric aerosol, which have impacts on air quality, climate, and weather. We have two more definitions here: friction velocity and threshold friction velocity. Friction velocity is the measure of wind shear at the surface, and threshold friction velocity is the minimum friction velocity required for wind erosion to occur. We have different standards to classify dust particles by size. So we have different systems for classification of particles by size. But according to Shaw 2008, we usually call particles with diameter, with diameters less than 63 micrometer, which are mostly clay and sealed as dust, and particles with diameter between 63 to 2000 micrometer as sand. The particles with depends on their size. They usually adapt different modes of motion in the atmosphere, which we have suspension and saltation and creep. Is it working? Okay. So really fine particles usually remain suspended in the air for a long time, but a little bigger particles with diameter between 20 to 70 micrometer usually remain short time, like kind of several hours. And then particles with diameter between 70 to 500 micrometer usually be part of the saltation process, which I'm going to talk about saltation later. because it's the main process. And then the heavy particles with diameter bigger than 500 micrometer usually creep. It means that they are heavy, they are too heavy to be lifted by the wind. So they're gonna push along the surface by wind, or maybe saltating particles. We have three major mechanisms of dust emissions. First one is aerodynamic entrainments, which means that particles can be lifted by wind directly. It means that we don't need saltating particles here. So just keep in your mind, for fine particles, the interparticle cohesions are stronger than the gravity and aerodynamic forces. So we can say generally aerodynamic entrainments are small. But the second mechanism will be saltation bombardment, as saltating particles, which could be aggregates or sands, strip the surface. They have localized impacts, which is strong enough to overcome the binding over the particles. So we're going to have dust emissions. And then we have aggregate disintegration, which is as important as saltation bombardment, which means that under natural conditions, we can have aggregates. So by wind or by saltating particles, these aggregates can be disintegrated and create dust emission. So our goal of a study is to examine the applicability of dust emission scheme developed by Shao 2004 to model dust emission for a crusted surface in New Mexico for three major events. And our objectives are evaluate the capacity of a scheme in predicting the magnitudes and temporal evolution of dust emission for a crusted surface, and also detect and address potential deficiencies of the scheme to enable dust emission modeling for the crusted surface in future. So let's have a quick overview on the studies that have been done about the dust emission schemes, and also I'm going to have a deep look at the Shao scheme, which is the scheme that I worked on. Studies about dust emission has been started from 1980s, probably 30 years ago, and the first schemes that has been developed by Gillett and Pasiano, so Machikrena and Pargametti, sorry for the weird pronunciation. They developed some empirical and semi-empirical dust emission schemes, which was for bulk dust emission. It means there wasn't any information about the size of the particles that were emitted. So then Shao and Alfredo and Gomez started working on some physics-based model. These were size-resolved dust emission schemes, and we had information about the size of the emitted particles. And the main mechanism of dust emission in these schemes were saltation bombardment. And then we had, in 2004, Shao developed another scheme that I'm going to talk about this later, because this is the one that I chose to work on. And then later on in 2014, Koch et al. And Close et al. Worked on some other dust emissions, and they tried to include some other dust emission mechanisms in their scheme. So let's have a quick review on the dust emission models. Dust models are the key components of the wind erosion modeling systems. So here you can see a general structure of the dust emissions. We're going to have some inputs, and we're going to calculate the key variable here, which is threshold friction velocity, which depends on soil texture, vegetation cover, and some other factors. And then we're going to calculate saltation flux for each particle size, and then for sure the total saltation flux, and saltation flux will be used to calculate dust emission rate for each particle size, and then we're going to have total emission. Here, let's get back to the Shao's scheme. In 2004, Shao developed a dust emission scheme. It was physics-based scheme, and for both aggregate disintegration and saltation bombardment. This this dust emission scheme is based on the volume of dust that has been emitted. It means that it's volume based. And then I just want to mention that this scheme is proportional to siltation flux, but this proportionality it depends on the soil texture and soil plastic pressure. We have three major factors here. One of them is three major parameters here. One of them is bombardment efficiency, which is the ratio between the mass of the ejected by bombardment to the mass of impacted particles. And then we have sigma of P, which is the ratio between the free dust and that of the aggregated dust. And also we have gamma here, which shows how aggregates release and break up. So these are some main parameters of these schemes, but for sure I introduced some of these parameters in last slide, but here I want to talk about one of the main parameters in the shower dust scheme, which is minimally and fully disturbed particle size distribution. When we are talking about fully disturbed, it means that the disturbance is enough. When we are talking about minimally disturbed, it means that the disturbance is not enough to break up the aggregates. But when we are talking about fully disturbed, it means that disturbance is strong enough to break up all aggregates. So we can use mechanical forces or we can use chemical things. So let's go through this study area. I just want to mention for this project, I wasn't involved in gathering data, so I used the data. All the data was provided with Martina Klose. And then in our study area, which is located in southern part of New Mexico, we had some meteorological instrumentation like rain gauges, wind vane, anemometer, thermometer to collect meteorological data. And we had some instrumentation for sediment flux measurements like the NWEC, Sentries, and then we had BSNEs and some other samplers. Here you can see some pictures of the study area. You can see that our area is partly crusted. So let's go through numerical experiments and results. I put these two together because it's going to make it easier to follow up. First of all, we worked on soil particle size distribution. This is the common way to represent soil particle size distribution using the model as sum of 4 log normal distributions. We usually use this equation, and then we're going to fit our data, observational data, with this model using nonlinear least square methods. And then we're going to get some factors. We're going to get some parameters here, and these parameters will be used as coefficients in the model. You can see one of the examples of these fits here. Here we have particle size distribution of soil at our site for crusted surface, and this red line, as you can see, red line is the fit line, and the black line shows the observed data, and you can see that the black line has been covered completely with the fit line. It means that we got a really good fit with the observational data. Here, I just put these two together to show you the minimally disturbed and fully disturbed particle size distribution together to have a comparison between them, and you can see that there isn't much difference between the fully and minimally disturbed in our area. So then we try to run model with the default setup. When I'm talking about default setup, it means that these dust emissions have been tested against different full measurements, so they have come up with some numbers for the parameters, which shows that if we use those, we're probably going to get better results. So we started with those default parameters. These parameters comes from like kappa that we have here in the gamma, and then plastic pressure that we have here. So we use these numbers and we ran our model for our area, and then you can see I just put 2 events here. I have worked 3 events. I have worked on 3 events, but I just put 2 events here as an example 23rd of March and 25th of April. A red line shows the model and model results, and the green line shows the observational data. And you see, by running the model, just using the default setup, the model was really overestimating the observational data. And then we used some data from Sentry's about saltation flux to compare our observational data with the simulated saltation flux. Sentries are some instruments that we use them to collect saltation flux. So when we were comparing the model to observational data, we found that the model is overestimating saltation flux by 3 orders of magnitude. So we found that we need to scale saltation flux for our model. So we started working on that. We scaled saltation flux by a constant factor, by a constant number, which is 1,000 divided to 1,000, and then again we ran the model with the default setup, and then we found that right now, the model is underestimating the observational data. So it wasn't unexpected because, first of all, saltation flux was overestimated because we have limited supply of saltating particles in our area. And then we found that, as I showed you in the last slides and previous slides, there is a little difference between the fully dispersed and minimally dispersed particle size distribution. This is because of the cross surface. It means that we have a little cross surface in our area that was underrepresented in the particle size distribution because it's thin. So and the dust emission usually happens on the surface of the crust. So we are going to present the thin crust surface in our data to have a big difference, to get some difference between the fully dispersed and minimally dispersed particle size distribution. So we decided to replace fully dispersed particle size distribution with crust particle size distribution. And then again, we ran the model with default, and then we started working on the other parameters that we have, like saltation bombardment and also like gamma, and we got substantial changes in our data. Let me show you from the picture. Here, we have 23rd of March 2016 here, and then we have another event here. So in this graph, you can see that we have already scaled saltation flux, and also we have worked on the other factors and other parameters of the dust emission scheme. But you can see still the model is underestimating the observational data. But here, for the same event, we tried to replace fully dispersed particle size distribution with the crust particle size distribution, and then we worked on the parameters that I was talking about. And then you can see how well the model is predicting the observational data. Again, here for the 26th of April 2016, you can see that here we have a scaled saltation flux, and we have worked on the parameters of the scheme, but still model is a little bit underestimating the observational data. But with replacing the cross particle size distribution, they're representing the soil well, so we are getting really good results on our model. So the model is well estimating the observational data. So to wrap up the results, I just want to say that this is just the preliminary results. So I'm going to work more on the loose erodible materials. We have to work on some other crusted surfaces, and to see how these parameters of the schemes going to change in different surfaces. And we need further information actually from the other areas to test our model for different crusted surfaces. And At the end, I just want to say that the dust emission models are the key parameters, are the key components of the integrated wind erosion dust emission system, so wind erosion modeling system. So it's really important to have an accurate estimate of dust emission rate to get the best results for dust storms prediction. Thank you.
Are there any questions?